When dealing with problems in physics where you are accelerating, you'll often find yourself in a scenario where you have to solve a quadratic equation. Let's look at a quick example. In this case, we have a ball, and it's thrown from the ground upwards, and let's say it lands on a ledge. It's going to go up, it's going to follow this trajectory, and it's going to end up at a different height. Now, if you were to mark its positions, you have an initial position of 0. We'll call its final position at 5 meters. We'll give it a velocity of 15 meters per second, and you're dealing with gravity as the accelerator, and so it's negative 9.8 meters per second squared. Now, in this situation, we can write out our position function, which follows the form of x final is 1/2 at squared plus b initial t plus x initial. And we would plug in our values. You get 5 equals half of negative 9.8 is negative 4.9 t squared plus 15t plus 0. And as you can see, the only variable we have is to solve for time. And this would be the time that the object is at a final position of 5 meters. So in algebra class, you would move the 5 over to the other side, set up the quadratic formula. But I want to show you another way to do this rather than using the quadratic formula. So look at solving by graphing. So in this case, I'm going to open up my calculator. There's two ways to look at this. One is to look at this as the function position as it relates to time is equal to negative 4.9 t squared plus 15t plus 0. And what I really want to know is, well, what is the position at a position of 5? What is the time? So when x of t is equal to 5, what is t? And so one way to do this is to graph the function y equals negative 4.9 t squared, and then calculate, you're going to have to use x, plus 15x plus 0. And when I graph this, let's see what our scale looks like. You're going to get a parabola. Now, we can look at our window. We can adjust the fit. We can change the maximum y scale. Maybe we move to 20. And when you graph it, you now can see the full top of the parabola. What we really care about is, well, when is equal to 5? So if I just graph a line at y equals 5, and I graph them both, you'll see that line will cut through here. And it kind of looks like my picture. And what I really want is, what are those intersects? So second calc 5 will give me intersects. Now it looks like it intersects that height of 5 on the way up. Now in my picture, I really want what's on the way down. So I'm going to select the intersect on the right side. Select that curve, select the second curve. I'm going to take a guess, which is right about where I'm at. And you can find that the x value, which is really t, is 2.68 seconds. T equals 2.68 seconds. That would be the time that it reaches that height of 5 meters. Now, most of you guys learned another way to solve by graphing. That's to set it equal to 0, in which case the other option would be to isolate that equation, negative 4.9 t squared plus 15t minus 5. And what you're effectively doing is you're taking that first function and you're shifting it down 5 units. So instead of just plus 0, I'm going to subtract 5 from it. And I can get rid of this function. And when I graph, it's the same parabola, but it's now shifted lower, so that the height we care about is now on the axis. And rather than finding the intersect with the line at 5, I can do second calc and find the zeros, option 2. And again, it looks like I want the one that's on the right. And so I can click left of that one, scroll all the way past the 0, click the other side, and then take a guess, and I should get the same value. So again, when the vertical axis is 0, the time is 2.68 seconds. Now, some of you guys realize there's actually 2 times associated with this. If I want to go find that other time, second calc, 2 for 0, and I scroll to the left of the 0, which is going to be over here, the left bound, and and then the right bound, and then back to the 0, I get 0.38 seconds. So I actually get two positive times, one of which is on the way up, 0.38 seconds, and the other one is on the way down, 2.68 seconds. So it's important to look at that from a physics standpoint and determine which time actually makes sense for this problem. If I want to know when it lands on the pedestal, I want the one when it's coming down. If that's a window and it's going upwards and breaking the window, it's going to break it on the way up, in which case the time that it would break it would be at 0.38 seconds. So part of answering the question in physics is to use the math to find the time at which that object is at a particular height, and then interpret that answer based on what is happening in the problem, which again is why we want to typically draw a good picture before we start getting to work. Hopefully this gives you a little bit of a recap of how you might solve a quadratic with graphing using a picture. And again, it's sometimes helpful to see the graph kind of looks like the picture I'm drawing. It's a good way to solve them rather than using the quadratic formula. I can get the same two roots, in this case 0.38 seconds and 2.68 seconds, that are my possible solutions. Hope this helps.